you don't know, give a good guess, okay? If there's an answer that you've heard that you disagree with or you're not so sure about or something like that, then say something and we'll discuss it. Is that fair? Okay? I think there'll probably be some that we don't need to talk about in full, so that's why I want to do this. So I'm going to start with you. Is that okay? No pressure, just because you're on, it's like at a nice, natural starting spot. Okay. So no pressure. Again, I want to be clear. You don't always have to be right in here to say something, okay? We're learning by community. That's what we do. All right. So, number one, which of the following quantities is a scalar? What did you say? What did your group say?
Distance.
Said distance. Do we agree? B? Yes? No? Do you want to discuss?
Yeah.
Talk to me.
I agree, but why is it not weight?
Why is it not weight? Anybody did not have weight and tell me why? What's that?
It's a type of force.
It is a type of force.
Yes.
Weight is just a different name for the force of gravity. Yeah. So weight is the force of gravity. The force is a vector. There you go. Yep. And as we're going through this, I'm also going to let you know that I am teaching this course in kind of the mindset that you're coming in with some knowledge from accelerated physics. If there's something that I'm talking about, you're like, I don't know what you're talking about, then ask, please, please, please. Okay? Yeah. And that's what I'm saying. And not just you. There are lots of you. Like, some of you haven't taken this class for a long time, right? I haven't seen me for a long time. So ask questions. Yeah.
So would it be a scalar if it were mass, not weight?
If it said mass, then yes, it would be a scalar.
Okay.
Good question. Yes. So everybody's good on one, yeah?
Mm-hmm.
Awesome. Number two, Cameron, go. B, she says. We agree?
Mm-hmm.
It is B. And if that was just a lucky guess, then cool. Okay? And we'll talk about that stuff later too. I'm not going to stress out about that. Number three. What did you say? D, she says. Do we agree?
No.
Okay, should we go through it quick? Okay, this one it's not a super scary one, but there are a couple pieces here that may have thrown you off, or maybe not. We'll find out. So it says, gravitational field strength is expressed in newtons times, it says kilogram to the -1. First of all, what does that mean?
1 over kilograms.
1 over, right? Is everybody okay with that? Negative exponents just mean it goes in the denominator. So this is going to be, oops, go smaller, thank you. N over kg. And then we have to remember what in the world an N is. An N is a Newton, right? Yeah. A Newton is a measure of...
4 kilograms per times acceleration.
Yeah, that would be its equivalent. It's a measure of force, right? And a force we might remember as a kilogram meter per second squared. If we think about it, and how does she remember that? Well, part of it's just they do this a lot. But if like the easy way to remember that is that, remember F equals MA, and M is kilogram, right? That's a mass. A is meter per second squared. So this is going to be, if I'm just going to write it out in raw stuff. So we've got excuse me. Let me write this in units. So it's going to be a kilogram meter per second squared divided by kilogram. So what's going to happen to those kilograms? They're going to be gone. See ya. And so we're left just with meter per second squared. So it should be B. Is that okay? Is that cool? Okay. What's that?
Why is it the -2?
Because, well, and this is an IB thing. So remember I was telling you like the whole AP IB thing. IB is really, really into, for some reason, writing their exponents as, instead of like underneath, but writing them as negatives. So that it's all on one line. I don't know why. Because they're quirky and cute like that, I guess. So hold on, let me move it up. What's that? Quirky? Yeah. So MS to the -2 just means, I mean, this transition here is the same as this transition here.
Oh, gotcha.
Is that okay with everybody? Do you see what I'm saying?
So if you're going to do it without an exponent, what would it look like?
It would just, well, it'd be meters per second squared. But I just don't want a denominator. They're scared of denominators. They're kind of like third graders.
So
They're like, oh no, it's a denominator.
Okay.
Is that okay? Does that make more sense? Okay, awesome. To be clear, I'm laughing at third graders, not at you.
Yeah,
okay.
That's it.
I think it's funny because third graders get afraid of denominators. Sometimes high school students do, but don't admit that to me. All right. Let's go to the back. Miss Ann, do you want to do number 4?
I think it's C power.
Think it's C power. What do you guys think?
Yeah.
It is C power. If you were like, I don't know what electric field is, well, it's, all right, we'll get there eventually, okay? Acceleration definitely is a vector. I'm going to give you electric field as a vector. We know momentum is a vector, right? Power is all that's left. So yes, that's one way to look at it. You ready?
Yeah.
Number 5, what'd you get?
Okay, I think it's A.
Thinks it's A. He's like, you're like at a game show, right? I'm gonna go with A. Come on, big money. What do you guys think? Did you agree with them?
Yeah.
Does anybody want to go over that one?
Yeah.
Yeah.
Okay, let's go. It is A.
Yeah.
Nice work. Let's go through it. All right. Oops, I don't like that kind of pen. Hold on. Sorry. Blue. That's pretty.
Does this have to do with like the unit circle? Kind
In that it's on a circle, but not really.
Like,
I mean, like, yes and no.
with like pi and everything and like.
If you don't love the unit circle, like if you have unit circle hate issue, like you need to go see a therapist about unit circle stuff, then no, it has nothing to do with unit circle.
But if you do know it, could it apply to it?
Kind of. Let me draw this picture in a different way than it is there. So there's my axes. Here's P. Here's Q. Yes? Okay. This distance is A. This distance is A. All I want to know is this distance. That's it. That's it. What? So why did they draw all that other stuff? Well, let's figure that out. Instead of just like they were trying to trick us. No. So a car did. It actually traveled around the circle. Good for it. Okay? We don't really care because the word says displacement. Yeah! Not distance, right? Distance is how far the odometer clicks. Displacement is GPS point to GPS point, right? Does that make sense? Okay, so it's one point to another. Now are we okay?
Yeah.
Okay, fantastic. Number 6 back there, Michael, go! Do you have any idea? And you can say no. This one is a big one.
B looked kind of nice.
B looked kind of nice. That is an educated guess, I would say, based on the way that you said it. Yeah? Yeah? Okay. This is a big deal, so I want you to write this down, whether this is in your notes or on here or whatever, because we're gonna push this a lot. So the game is how to make a straight line graph. Do we like lines?
Yeah.
Yes, lines are easy, right? Square roots, signs, like who wants all that stuff? Not me. Let's do something easy like a line. So the game is when we do labs to get things so that we can graph things to make a line because we can describe lines really nicely. If you wanted to have a line, you might look at the equation for the line as y equals mx plus b. Would you agree? That's familiar to everybody, right? Y equals mx plus b. If you have it in this form, boom, you've got a line. Now, if you look at the equation that's written in front of you, that does not look like a y equals mx plus b. Would you agree? There's a square root, there's like fractions, like what is this? It's ugly. So we are trying to get that thing to look like this. Right now, it does not. Okay, so this is like transformational equation fun time.
Oh boy.
It's really not bad. F is equal to 1 over 2 pi times the square root of m over k. Yes?
Yes.
Oops, I wrote that backwards. K over m. Excuse me. Okay, now, the two things that they said we measured or that we want to relate are F and M. So right now we have F, and that kind of matches up. Do you agree?
Yeah.
It kind of matches up. There's one there, and there's one there, and there's an equal sign. So there's one thing and then an equal sign. So that's good. Then we got nastiness and square roots. And this K is going to be constant. Does everyone remember what that constant is? It's a spring constant, yeah. Yeah, nice, because it's spring stuff. Yeah. Right? Yeah, it's gotta be. And then the M is in the denominator in a square root. Yuck. Now.
Oh, so it can be K and it's negative.
So yes, there's something we gotta think about, right? So, Michael, you suggested B. You thought that one looked kind of pretty.
Yeah.
Can you tell me why?
Well, I was trying to relate F to M.
Uh-huh.
I figured, well, if you square everything, F becomes to the 2 power.
Yeah.
And that goes away. And then if you take 1, and M's in the denominator, so 1 over M, M's still in the denominator.
It's a beautiful thing, right? Let's try it. Let's try, I need to write it out because I'm not quite that, like, visionary, but good for you. So I'm going to square both sides. Is everybody okay with that? When in doubt, if there's a square root, square it. Because it gets rid of the square root and then we don't have to look at it anymore. I mean, not that we're trying to say they're ugly, but, okay, so f squared is equal to, so that's going to be, I'm going to write this as k over 2 pi squared. Is that okay? Times 1 over m. Is that okay with everybody, what I just did there?
Yeah.
So I did like a lot of algebra at once. I like to do algebra, so, but tell me if I'm going too fast. Now, take a look at this. This is so cool. I'm going to pick this thing up. I'm going to move it up here. Right? Well, it's kind of cool. It doesn't really line up super well. We'll put it there and we'll just pretend. Okay. And then we'll get ourselves a new color, maybe just a blue. And we'll notice that this stuff now matches up really nicely. And this doesn't really, like it's not lined up. That's what I'm sad about. That's kind of the same thing. Do you see what I'm saying? Yeah? Donna's like, no, I don't see what you're saying, you crazy lady. What are you talking about? I'm going to get rid of it. Let me write it over here again. So y equals mx plus b. That's what I'm looking for?
Yeah.
I have f squared is equal to some nastiness. That's the k over blah, 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 times 1 over m plus 0. Is that okay?
Oh, okay, so the plus 0 is
The plus 0 is the b. So now, I've got some nastiness that's going to be my slope.
oh, okay, that makes sense.
Right?
Yeah.
So if I put f squared on one axis, probably on the y-axis, and 1 over m on the x-axis, I got a line. We love the line, right? So good educated guess. Thumbs up for that. All right, there you go. Moving on. Number 7 was about the stuff we talked about last time. Casey, what did you say? B, he says. What do you think?
Yeah.
You okay there? Yes, absolutely. It is just random errors. All right, I don't know where to go next. We're going to go over here. Is that cool? Number 8. Number 8, a vector v makes an angle theta. Whoa, there's lots of scariness, but can you do it? What did you say? B. Do you guys agree? We okay? Yes, no, we're not so sure. Like, oh, no. Want to fight about things? Okay, let's go through it. Fighting. Here we go. So here's my angle theta. And it says, and so I need to read this carefully, as the angle theta increases, so that means we're going, whoa, hello. I don't know why it likes to do that on me. It's annoying. There we go. So we're going that way. Does that make sense? It wants to know about the x component and the y component. So it wants to know about this piece here. What's going to happen to that piece of this right triangle as this goes up?
Yeah.
Does that make sense?
Yeah.
Yep.
It's going to get littler because so if I draw another version of that, like up here, then it's going to only go to there. Is that okay? So the x part is going to decrease, but as the x part decreases, what's going to happen to the y part?
It's going to increase.
Yeah. Okay. So that would be C. All right. Are we doing okay? We're happy? Okay. All right. Number 9. Well, I'm not going to make you do all of number 9. In fact, I'm going to take you off the hook unless you want to answer A for me. A1. Did you guys come up with that? And if you say no, that's totally fine.
We tried.
Okay.
Tried.
Okay. So you're going to pass and I'll come back to you?
Yeah.
Okay. All right. 9A1, what quantity is given by the gradient, which is a fancy term for slope, of the graph? So we're just gonna look at the x and the y-axis, the x-axis, right? Y-axis is
Centimeters.
centimeters. X-axis is
Second square.
second squared, so it's going to be centimeters over second squared, which is a measure of.
Acceleration.
Boom. There you go. A2. Explain why the graph suggests that collected data is valid but includes systematic error. Raise your hand. Yeah, go ahead.
Because in 0 seconds it starts, it's already gone 1 centimeter.
Right. Is that logical? Do you guys see what he's talking about? If you draw a best fit line in there, the y-intercept would be not 0. That's a problem. That means that it's jumping, like it's, no, it's not right. So that's your systematic error. Number 3, Do these results suggest that distance is proportional to time taken squared?
Yes.
Yes or no? What do you think?
Because as one increases, the other increases.
Okay, so I'm going to tell you the generally accepted answer, and then I'm going to say but. So I would say, yeah, they look like they're proportional. Not even just as one increases, the other increases. Because you could have, here, I'll write this on the board.
You could have
like a parabola, right? As one increases, the other increases. But they're not increasing proportionally. So to me, the definition proportionality means that as one increases, the other increases the same amount, right? So, But, IB friends are going to put their little IB hats on, okay? And pay attention to this. In IB, they are very, very picky. And for them, proportional means it also has to go through the origin. Okay, let me say that again. In IB, so if you're an IB kid, you need to write this down so you don't forget. Proportionality means that it has to go through the origin. It's one of those little picky things that they've decided they're going to, jump on. I don't know why.
So
Now, what's that?
So it would not be.
So it would not be proportional. Correct. Now, A4, I'm not going to spend time doing this right now, but I just want to make sure this makes sense. Making allowances for the systematic error, calculate the acceleration of the object. Can you do that? How do you find the acceleration?
You the slope, you just find the slope
And then you multiply it by.
What's that? No, you just find the slope.
Yeah, you found the slope.
Just do it.
Yeah.
Just do it. Just find the slope.
I agree.
So,
I was confused by when it'd be a parabola shape since it's growing and it should be accelerating. Oh, because it's over second squared.
got it. Oh, yeah.
Oh.
That's what. So they did in number 9. They did the same thing that we did in number 6.
They found a way to make it.
Right? They linearized the graph. So they found a way to make it a line because we like lines and we can find the slope of a line really easy with no calculus needed.
Would you define the parabola there? Would you define that as proportional or not?
No, this is not.
No.
No.
Okay.
This is increasing, but that's all. That's what you would say. Okay. So now I want to look at B really quickly. Oh my goodness. Okay, really quickly. So the following graph shows the same data with uncertainty. So remember we talked about uncertainty. And we now know how to calculate uncertainty or figure the uncertainty. So do you see the little error bars that exist on this picture? So the error bars that exist are graphically representing those things that we now know how to find. Now, when it asks you to find the uncertainty ranges, what are we doing? Adding 2 lines to show the possible acceptable values. So here's the thing, and this is a little bit funny, because this is something that if you've not done this before, you're going, oh, that's kind of interesting. And if you have, you're like, that's brilliant. Now we are free to, acknowledge our error and embrace it. Right? Remember I said that error, it's a good thing. We love having error because that means we don't have to be perfect. It's good. We're going to try and measure the acceleration due to gravity later this next week, I think. Okay? And when we do that, we're hoping to get a value that's close to... It's true, but we're not going to. Just saying, okay? You probably, unless, well, no, you're not. You won't get it, okay? When you don't get it, you're going to be like, oh, I'm so sad. I didn't get 9.81 like I thought I was supposed to be. But you don't have to go home and cry because you've got these error bars. And as long as your answer is within error bars, you're set. So you're going to linearize your data. So there's some data, and there's some data, and there's some data, right? And let's say you took really lovely, precise data, so it's all in a line, and you've got these really, really nice error bars. You can draw your best fit line. But let's say your best fit line is like 13. A little bit too big, right? Too high of an acceleration. You can then draw 2 other lines to show your range. So one of them is going to go from the top of this one to the bottom of this one, and it's going to go through all of them. You see what I'm saying? That's a much lower slope. And then you can do another one that goes from the bottom of this one to the top of this one. A much higher slope. And then you've got a huge range in which that value can fall. And it's not like this is cheating. That's the cool thing of it. It's not cheating. It's acknowledging that you're not perfect. That your measurement tools are not perfect. That's okay. We're okay with acknowledging that. Alright? Does that make sense? So one could do that. We get it? Alright, we're going to go. Keep going. I don't like early at Wednesdays. Number 10. Now, my friend Will.
Yeah.
You're back. No excuses now.
Oh gosh.
Right. Or, it's okay if we're wrong because we like to embrace learning. Number 10. What did your group say?
We all said C.
You said C. What do you guys think? Do you agree with him?
Yes.
Yay! Good for us. All right. Number 11. Let's go. A question?
Yeah.
Go.
If you're multiplying it times an area, can you just add them? Like,
Yes, but then it's the percent uncertainty. So you're not just going to add the values. No, you're not going to add the errors. Does that make sense?
Yeah.
Yeah, it's a little subtle thing, but it does make a difference. Yep. Number 11, Peter, what you got?
I got D, but I'm not that confident.
Okay, that's fair. That's fair. What do you guys think? Do you agree with him?
Yeah.
Should we go through it? Would that be helpful? This one I thought was kind of ugly, so let's do it just to make sure, because I want everybody to feel confident about it, because you may see one of these in a week or so that you need to know how to do. Just saying. All right, here we go. So we've got a time of 2 seconds, plus or minus 0.1 seconds.
Yeah.
And we know the displacement. This one's kind of a backwardsy question. 1/2 GT squared. And we got a value for the depth of 19.62. And we want to know the absolute error. So we want to know the plus or minus what in terms of the depth. Does this make sense to everybody? So the only measurement that we made, we're assuming that G is correct and accurate, so we're not going to worry about either of those things. We have an exponent, so what are we going to do with that exponent?
We're going to multiply the uncertainty.
Multiply what kind of uncertainty?
No.
Oh, sorry.
Look at your chart, guys, look at your chart, just to make sure, because you're all like kind of guessing 1 of the 3 and it's a 33% chance. The percent uncertainty, so we have to figure out the percent uncertainty first, right?
Yeah.
So we're going to take it, I want you to do this right now, even if you did it 5 seconds ago, I don't care, do it again, just so that I feel good about it. So you're going to do delta T over T times 100. So what's the percent uncertainty in time? What'd you get for the percent uncertainty in the time? 5%? Do you guys agree with him? And I think many of you know this, but if you don't have a calculator someday, if you just forget to bring one or whatever, I do have calculators on my wooden table in a box of them, so you're always welcome to borrow one if you need one. Okay, so we have 5% uncertainty in my time. So what's my percent uncertainty in D going to be?
10.
Does that make sense? Because I'm multiplying it by 2, multiplying it by that. So I can say that the percent uncertainty, so that would be delta D over D times 100 is 10%. Is everybody okay with that? Now, what am I looking for? What's my goal? What am I trying to find?
The error and, yeah.
This guy, right?
Yeah.
But I know this and I know this, and I'm going to plug this number in for D, and then I can solve for delta D.
Oh.
Does this make sense?
Yeah, could you 10% of that 19.62?
Well, that's really what you're doing.
Yeah.
Yes. Yeah. So yes, again, different route. Yes.
You double the 10% or 5% because of the 1/2?
No, because of the squared.
Oh.
Does that make sense? Yeah, good question. So what do we get then? We get 2, don't we? It's like 1.96 something. Yeah. So within sig figs, you've got plus or minus 2 meters to go there. So you were correct. Good job. Yay. Little flag. Woo. All right. Jack? 12? He says with an air of confidence that can be equated to, like, I don't even know, a snail's trying to run a race or something right there. Okay. Do you guys agree with him?
Yes.
With as much confidence as he had, or a little more even, maybe?
Quite a bit more.
Quite a bit more. Okay, let's see if we can give him as much confidence as we have. Let's see. The percent uncertainty in the measurement of mass is 0.5%. The percent uncertainty in the measure of length is 1. The best estimate for the uncertainty in the density is, did you actually have to calculate the density to figure this out? No. You need to know how to find density, right? You need to know that density is equal to
Mass over volume.
mass per volume. So what are you going to do with these things?
You're gonna.
You have to square.
Add them, but, right, it doesn't list the volume.
Cube the length.
Yeah, so we're actually going to write this as mass per length cubed. So you're going to cube the so you're going to take the uncertainty in the length, multiply by 3. So 1 times 3 is 3. And then add 0.5 to that, and then you're set. Is that okay? Hold on, don't leave me yet. I know we're getting close, but... What? What'd you say? Nothing. Red, I'm sure. Okay. I'm going to let you know where we're at because we got through all of the review stuff we got. We did not obviously get to any new material today. We need to. So, on Friday, when I see you, we're going to move. I don't want to say fast. I don't want to intimidate you like that, but I want to let you know that if you know what a force is and you know how forces work, that would be really awesome. And if you are familiar with velocity and how to do velocity problems, that would make things go faster. So it's the beginning of chapter 4 and the beginning of chapter 2. If you already read it once, maybe read it one more time just so you got it in your head. We are scheduled to have some sort of assessment next Tuesday. I will tell you what that will look like on Friday. Does that make sense? Looks like I don't know yet. You can all figure that out. Yes, ma'am. Homework chapter 2. Chapter 2. Yes, thanks for clarifying. The homework listed on the homework sheet is from chapter 2, not from chapter 4. Okay? Other than that, I hope you have a fabulous day. I will see you guys later.
Thank you.
I'm going to call you Donnie G. Donnie G.